Without computing devices, there are many calculations which would turn difficult, especially with curves. A method to simplify the equation is called linearization. Know more about the procedure here in differential calculus. Linearization is the conversion of a higher degree equation into simple x and y or linear function, thereby making it easier to evaluate the function and determine the variables. With the curve on the plane, linearization starts by drawing the tangent line at a specified point. Say that the point is at coordinates x and y. To find the equation of the tangent line, use the point-slope equation, which is y minus y1 is equal to m times x minus x1, where y is the function of x, and this is denoted as the linearization of x in the process. So the equation turns out as L of x minus y1 is equal to the slope m times the quantity of x minus x1. With multiple points involved, let us place the point under consideration with the coordinates of a and f of a. If we take another point at b, which is close to the first, note that the alignment of the tangent line and the curve is almost the same, which would show that we can approximate f of b using the tangent line instead of the curve. To come up with a general formula for the linearization of the function, where we have L of x minus y sub 1 is equal to m times x minus x1, from the last derivation earlier, we note that y1 is f of a, and x1 is a. The last parameter to work on is the slope of the tangent line at a, denoted as m. In calculus, m is taken as dy all over dx, simplified as y prime. And going back to the graph, we get y as f of a, so we can say that y prime is f prime of a. Have this plugged into the equation to get L of x less f of a is equal to f prime of a times the quantity of x minus a. Isolate L of x by transposing the other term to the right, and we get linearization of the function of x is equal to the function of a plus f prime of a times x minus a. There are different applications of linearization. They are used in polynomials where the initial value is given. They are also used for roots where the initial value may or may not be given. Another application is through exponential functions. The succeeding videos will showcase examples of each type. With any given polynomial, root, or exponential function, linear approximation follows a specific algorithm, the first of which is to identify a point to take the tangent line with. Next is to find the slope of the tangent line using derivatives. The equation of the tangent line is determined by completing either the linearization formula or point-slope formula. And lastly, the application is then used to evaluate the linearization with a nearby point. We start with some examples with polynomial curves having the function f of x equal to 3x squared plus 8. And we take the linear approximation at point with x equal to 2. We find the linearization first by using the L of x formula. From the premise, we have f of x as 3x squared plus 8. If we place x equal to 2, we get f of 2 as 3 times 2 squared plus 8, which is taken as 20. This is f of a. The next term we need to look for is f prime of a, which is taken as the derivative of f of x and simplified as 6x. At point x equal to 2, we get 6 times 2 or 12. By placing those two terms into the general formula, we get 20 plus 12 with x minus 2. Distribute 12 to the binomial terms, we have 20 plus 12x minus 24, which can be reduced to L of x as 12x minus 4. With the same function, let's check how the linearization is computed through point-slope formula. First is to locate the point of the tangent line. We know x is equal to 2, and y is solved using the function, which can also be written as y is equal to 3x squared plus 8. By plugging x as 2, we get the y coordinate as 3 times 2 squared plus 8, where y is computed as 20. Let's plug these values into the formula to have y minus 20 is equal to m times x minus 2. The only parameter left to solve is the slope. That is taken by working the derivative of the equation, where dy all over dx is 6x. With x equal to 2, the slope is then computed as 6 times 2, which makes m equal to 12. So to complete the point-slope formula, we have y minus 20 is equal to 12 times the quantity of x less 2, distributed as y minus 20 is equal to 12x minus 24. And the equation is simplified as y equal to 12x minus 4. The next example has the function in terms of both x and y equal to x squared times y raised to 7, and the point under consideration is at 2, 1. First, we use L of x formula. We place the x and y coordinates into the function to have 2 squared times 1 raised to 7, which turns out as 4. Next is to differentiate the equation with respect to x. So in such a case, y becomes a constant. Then, the derivative of the function with respect to x is y raised to 7 times the derivative of x squared, which is 2x. The derivative turns out as 2x times y raised to 7. With the final derivative with respect to x, we plug the point coordinates to have 2 times 2 multiplied by 1 raised to 7, which makes the derivative of the function with respect to x as 4. Next is to differentiate the function with respect to y, where we consider x squared as a constant. So the derivative of the function becomes x squared times the derivative of y raised to 7, which is 7y raised to 6. Thus, the derivative becomes 7x squared times y raised to 6. At point 2, 1, we get 7 times 2 squared multiplied by 1 raised to 6, simplified as 28. Again, the linearization equation is originally with only one variable x. But for the example where the function is both with x and y, the second term with f prime adds according to the different parameters, like one term becomes the prime with respect to x multiplied by x times x1, then the prime with respect to y times y minus y1. So the linearization now consists of 3 terms, but we have already determined each of the parameters, so simply substitute the solved values earlier into L of x. That is 4 plus 4 of the quantity x minus 2 plus 28 with y minus 1. Take out the parentheses by distributing coefficients to arrive at 4 plus 4x minus 8 plus 28y less 28. And by simplification, we end up with L of x is equal to 4x plus 28y minus 32. Let's move on to application of linearization, termed as linear estimation. Like we introduced earlier, knowing the tangent line equation at point A, we can approximate the y-coordinate of point B, as the curve and the tangent line are close together at that point. However, if we move further, like at point C, the approximate value lies on the tangent line, and it is far from the actual f of C, and the discrepancy is the error. Here is an example to show the application. With the function f of x is equal to 2x squared plus 2, we focus on x equal to 1 to approximate f of 1.14. With the L of x equation, we work with the tangent line at point x equal to 1. The function from the premise is f of x is equal to 2x squared plus 2. And when x is taken as 1, we get f of 1 becomes 2 times 1 squared plus 2, which becomes 4. For f prime of a, differentiate the function to have f prime of x as 4x. By substituting 1 into the prime equation, we get f prime of a as 4 times 1, which is simply 4. Now that the terms from the linearization are already identified, we get L of x as 4 plus 4 of x minus 1. Or that is simplified as 4 plus 4x minus 4, which is also 4x. This is the linearization of the function. Next is to approximate f at 1.14. And this is done by simply replacing x by 1.14 in the equation to give 4.56. The actual f of 1.14 is solved by substituting 1.14 into the original equation to get 2 times 1.14 squared plus 2, giving 4.6. From the two values, there is minimal error identified. What if with the same function, we approximate f of 1.6? With the linear equation of 4x and 1.6 plugged as x, we get 6.4. However, if 1.6 is directly substituted into the original equation, we have 2 times 1.6 squared plus 2, and that is equal to 7.12, showing 0.72 discrepancy or error. This happens because 1.6 is somehow far from 1.